We are Team Likas from the University of the Philippines, Los Baños. Likas is a Tagalog word that means natural, something inherent or not artificially made. Our mission is clear: optimizing concrete mix design for reduced environmental impacts and enhanced durability in coastal environments. Cement industry is responsible for nearly 8% of global carbon dioxide emissions. In harsh marine zones like spray-battered coast of Tampa, Florida, salt-laden winds and seawater penetrate concrete, corrode reinforcement, and accelerate degradation. The result? Cracking, delamination, premature failure.
Before we move to the two phases, we first define the parameters and methodology used in the study. The base case scenario that acts as the control variable uses cement as its binder. Meanwhile, the alternative case scenario that acts as the experimental variable utilizes fly ash, slag, and silica fume as partial cement replacement. Our LCA focuses on the cradle-to-gate analysis, extracting raw materials, producing them, and transporting them to the batching plant. For succeeding phases, concrete production, maintenance, and end-of-service life were excluded in the analysis. Following the cradle-to-gate analysis, we measured 5 environmental impacts. For the material sourcing, which will be used for transportation environmental impacts, the concrete mix components were sourced out based on the nearest site. First, cement was transported 21.6 kilometers away from Republic Cement to the university. Meanwhile, fine and coarse aggregates came from Terra Vera Corporation, just 24.7 kilometers away. Water transported just 3.1 kilometers from Lark has minimal transportation impacts. Lastly, admixtures traveled 17.1 kilometers by road from Timasif, Calamba. Supplementary cementitious materials have transportation distance fixed as shown. Meanwhile, for the service life prediction, we imagine a concrete seawall in Tampa Bay, battling saltwater every day.
We now move to phase A, where we optimize the mix proportion in preparation for base case and alternative case scenario. The index properties of the materials to be incorporated in the mix design includes the following. These were all retrieved in the batching plant or from UPL. To summarize, the final mix proportion of the concrete for both BCS and ACS are shown below. To break down the results of BCS in terms of LCA, the BCS has recorded shown below.
We now move to phase B, where we idealize the fly ash, slag, and silica fume ratio relative to cement content. The selection of the ideal ratio will be further distributed to 4 phases. By applying the stars and bars theory, where we determine the number of non-negative integer solutions to an equation, given by the formula shown, we can determine the possible number of combinations. When n is equals to 40, the number of possible combinations is 861. However, this is only valid if all variables has a maximum of 40%. Considering the max of silica fume is 15% and subtracting from total combinations, we can reduce the sample to 536 combinations. For the phase 2, we apply another constraint, which is the 15% minimum average reduction of environmental impacts. Using a redefined life cycle assessment, the samples was further reduced to 51 combinations. For the phase 3, these 51 combinations have their service life computed using Life 365. The results of both the LCA and Life 365 were analyzed with each other by computing their contribution relative to the highest value recorded. For example, using case 1 with fly ash being 40%, the contribution of EIR is recorded to be 100% since it has the highest EIR out of all the qualified samples. Meanwhile, it has a contribution of ACS-BCS ratio 80.2%, making the final average of 90.1%. For the phase 4, we select the final replacements of all SCMs based on their contribution. Out of all samples, a ratio of 38%, 0%, and 2% of fly ash, slag, and silica fume was recorded to have the highest contribution of 93%. Thus, the final cement replacement consists of 38% fly ash and 2% silica fume. Shown is the final components of ACS mix proportion with a breakdown of cement replacement as shown on the right side. To break down the results of ACS in terms of LCA, the ACS has recorded as shown.
The use of SEMs as a partial replacement for cement results in a significant reduction of environmental burdens in concrete mixtures, with an overall reduction of 15.74%. The greatest reductions are observed in global warming, followed by fossil fuel depletion and ozone depletion. Cement production is the primary contributor to these impacts. The calcination of clinker requires high amounts of fossil fuel, and the combustion of this material releases substantial carbon dioxide emissions, contributing to global warming, and nitrogen oxides, a major cause of ozone layer depletion. The toxic components of cement also contribute significantly to ecotoxicity. By reducing portland cement usage through replacements of fly ash and silica fume leads to 30.3% reduction in global warming emission, a 23.3% reduction in ozone depletion, and a 25.2% decrease in fossil fuel depletion. These reductions highlight the emission and energy efficiency benefits of SCMs. Improvements in ecotoxicity and carcinogenic impacts are comparatively smaller. While cement remains to contribute the highest impact to its toxic components, water is notably a significant contributor of impact for ecotoxicity compared to other categories, accounting for 30.832 CPUE per cubic meter of concrete. While fly ash partially reduces carcinogenic impacts, the use of silica fume introduces a minimal increase due to toxic impurities and trace amounts of respirable crystalline silica, or RCS, that may be released during handling or construction.
Here's the breakthrough. Our alternative mix outperformed the base case by a factor of 2.475. While the base case lasted just under 12 years before failure, the alternative mix delayed corrosion initiation to 23.5 years, achieving a service life of 29.5 years. The secret? Fly ash and silica fume team up to block chloride invasion. Fly ash acts like a concrete densifier. Its pozzolanic reactions plug pores and slow down chloride movement. Silica fume fills the microscopic gaps that even fly ash cannot reach, forming extra CSH gels to seal the microstructure. You might ask, why not use slab? While slab can offer chloride resistance, its environmental cost outweighs the benefits.
Simulations are powerful, but impact only happens when solutions are applied at scale. To evaluate real-world feasibility, we assessed 5 key parameters. Permeability is reduced in the ACS mix, minimizing chloride intrusion and the risk of cracking. Strength gain rate increases due to the synergy of silica fume and fly ash, accelerating construction timelines. Cost is reduced by replacing cement with highly available SCMs like fly ash and silica fume, lowering overall project expenses. Pumpability is slightly compromised due to the increased viscosity from high fly ash content, but this can be managed with equipment adjustments. Finishability improves as high fly ash content reduces heat-induced cracking, resulting in better surface quality.
Concrete builds our world, but it's also building climate crisis.
Cement is responsible for 8% of global carbon dioxide emissions.
SCMs like fly ash and silica fume lessen environmental burden and extend durability.
In coastal zones, we need concrete that resists, endures, and protects.
Our mix offers both durability and sustainability in one solution.
Let's break the mold. Reimagine concrete and cement the future that lasts.